Okay, last week, not last week, the last Tuesday we were solving this problem, but we didn't finish it because we didn't have time. So let's do it. So we want to determine the final temperature of this piston cylinder device. And this is the energy balance equation we got. And to solve this equation, we need to know the specific heat that should be evaluated at the average temperature. However, the final temperature is that what we want to determine. So we do not know the final temperature. We do not know the average temperature, so we cannot evaluate specific heat. So what we are going to do is that we are going to assume the final temperature and solve it, and we will check whether our the answer is meets the assumption or not. If it is not, then we are going to do a second iteration. That's what we are going to do. So the initial temperature is 17 degrees Celsius. So I guess the one simple way to find the specific heat is going to be, so 17 degrees Celsius is about 290 Kelvin. So if I assume that the final temperature is going to be 310, I'm going to assume that the final temperature is going to be 310. Then the average temperature is only 300. Then finding the specific heat at 300 is going to be pretty easy. So in that case, CP value is going to be 1.005. So the specific heat is going to be 1.005 kilojoule per kilogram Kelvin. So we are going to solve that energy balance equation. So initially, you can assume any number for the final, the temperature, because if it is incorrect, you can just go to the second iteration. Usually, within the 2 iterations, you will get the right answer. So in this case, we have 200 watt times 900 seconds, and divide by the mass of the system. What is the mass? I don't have it. What is the mass? I need to calculate the mass first. Okay. So let's calculate the mass. 120 times 0.3 divided by 0.287 divided by 290. Then the mass is going to be 0.4325. The mass of the system is going to be 0.4325 kilogram. Okay, then let's solve this problem. We have 200 watts times 900 seconds and divided by 0.4325 and divided by the specific heat, 1005. Then we get 414 plus 290, then we get 704. Okay, so if you do the calculation, you get 704 Kelvin for the final temperature. So we assume that the final temperature is 310, and what we got is 704 Kelvin. Are they close enough? No. So the first iteration didn't meet our expectations. So what we are going to do is that we are going to use this value as our second guess. So the second guess is going to be 704 Kelvin is our assumption. So let's calculate the average temperature. So what is the average temperature? 704 plus 290 and divide by 2, bless you, 497. So 497 Kelvin is the average temperature. Then do we have specific heat at this temperature? Yes, at 500 Kelvin, specific heat is going to be 1.029. 1.029 kilojoule per kilogram Kelvin. Then, using this specific heat, we are going to solve this energy balance equation one more time. So we have a 200 times 900 and divide by 0.4325 divided by 1029, and we get 404 plus 290, and we get 694. We get 694 Kelvin. Then, if you look at the the initial the assumption, we assume that the final temperature is 704 Kelvin, and what we got for the final temperature is 694. I think they are close enough. So we assume that we can conclude that the final temperature of the air in this piston cylinder device is going to be this value. So we assume that T2 is 704. And we calculated T2, that is 694. So they are close, right? So you end the calculation, you end iteration. Because initially we assumed 310 and we got 704, they are far away. So this is not okay. So we go to the second iteration, but we don't randomly choose another, the T2, but we use the value from the first iteration, for the second guess. And then do it again. Then you get the correct answer. So, yeah. So we calculated the temperature at the final state. Then based on that, we are going to calculate the entropy change of this air. So let's do that. We have an air. So we can use it's a constant pressure process. So there are three different ways to determine entropy change. The first one is S2 minus S1 is CV natural log T2 over T1 plus R natural log V2 over V1. That was the first equation. And the second equation was S2 minus S1 is Cp natural log T2 over T1 minus R natural log V2 over V1. And this time, the last one is S2 minus S1 is S degree 2 minus S degree 1 minus R natural log V2 over V1. So these are the three equations we can use to determine the change in specific entropy. Then, which one are we going to, oh, my bad, this is pressure. So this is P2 over P1. So which one? There's one more mistake. This one is also P2 over P1. So in our system, the problem is constant pressure process. So P remains constant. Then it is convenient to select the equation in the middle because we have a P1 and P2. Then what is, the natural log P2 over P1 when P1 is P2? That's a natural log 1, which is 0. So S2 minus S1 is going to be Cp natural log T2 over T1. Then let's calculate the change of entropy of the air. How can we do that? Mass of the air times specific entropy at the final state minus specific entropy at the initial state. Then this can be determined by this equation, mass times specific heat, Cp times natural log T2 over T1. What is mass? Mass is this one, 0.4325 kilogram. What is the specific heat that we used? 1.029 kilojoule per kilogram Kelvin. What is the initial temperature? 290. And what is the final temperature? 694 Kelvin. So from this, you can determine the change in entropy. If you do, you get 0.387. Okay, 0.387 kilojoule per kilogram. So we got that equation from the first two. These are when we assume constant specific heat. So these two are when we assume constant specific heat. If we cannot assume constant specific heat, this is the equation. So the second part of the problem is going to be, please calculate the change in entropy assuming variable specific heat. So we are going to use this last equation. By the way, we have a natural log P2 over P1 in the second term on the right-hand side. Since we have a constant pressure process, this one goes away. So the energy balance, so the entropy, the change can be determined by S degree 2 minus S degree 1. So the change of entropy of the system is going to be mass times S2 minus S1. This can be determined by here, mass times S degree 2 minus S degree 1. We already know the mass of the system from this ideal gas equation. So that is 0.4325. So this one is 0.4325 kilograms. So we just need to find S degree. Where can we find S degree? From table A22. In this table A22, what you can see is we have S degree here based on temperature. S degree here based on temperature. So what is the initial temperature? The initial temperature is, oh, do we have it? I think so. The initial temperature, 290. That's the initial temperature. The one that we calculated is the final temperature. So the initial temperature is 290. Do we have 290 in the table? Yes, right here. So that is T1. Then what is the S degree at this temperature? 1.66802. So this S degree 1 is what? 1.66802 kilojoule per kilogram Kelvin. Okay, no problem. Then what is the final temperature? We calculated the final temperature from this iteration method, and the final temperature is this one, 694. So let's find that temperature from the table. Where is it? Between these two numbers. So there is 694. So what is S degree at 694? Can you find that? Yes, by using linear interpolation. If you do, I don't have it. So you can find it. And this one goes here. Then you get the change in the total entropy. Again, 0.387 kilojoule per Kelvin. So either the constant specific heat method or variable specific heat method, you can see you can get the same value for the entropy change. Any question? Yes. Of this mass, because we want to calculate the change in total entropy. This S2 minus S1 is specific entropy, so per unit mass. So if you want to determine the total change, you need to multiply by mass to this entropy per unit mass. Okay? So this one is capital S. This one is lowercase s. So this lowercase s is capital S divided by mass. Any other question? No? Then we have one more problem here. We have an argon is compressed in an isentropic turbine from 2 megapascal and 500 degrees Celsius to 200 kilopascal. Determine the outlet temperature and the work produced by this turbine per unit mass of the argon. Okay, so let's calculate the temperature at the outlet. So how can we do that? We know it's an isentropic turbine. What is isentropic turbine? It means entropy remains constant. Entropy S remains constant between the inlet and the exit. So this is isentropic turbine. Then, is there any equation that we can use for an isentropic process? Yes, you may remember that we derived three equations, such as T2 over T1 is V2 over V1 to the power kappa minus 1, something like that. I don't exactly remember, but it was in the the lecture last Tuesday, so you can find them from the lecture video or on the PowerPoint slides. I don't have them. And what about the temperature pressure relation? I only know that one. That is T2 over T1 is T2 over P1 to the power kappa minus 1 over kappa. So this is the relation between temperature and pressure when you have an isentropic process. Okay? Since we have an isentropic process, we can use this equation to determine the relation between temperature and pressure. And by the way, what is kappa? Kappa can be found. Kappa is Cp over Cv. Then you can get this kappa, not K, from this property table. There's a kappa 1.667. That is for argon. So this value is 1.667. You can get this value directly from a property table. Then we know the inlet temperature 500. So we have an inlet temperature 500 degrees Celsius and the initial pressure 2 megapascal, in other words 2000 kilopascal, and we know the final pressure which is 200 kilopascal. So this one is 200 kilopascal and kappa is 1.667. So we have everything. Can you determine T2? Yes. No, there's a problem. What is that? Yes. So you cannot use 500 degrees Celsius in this equation. You have to use Kelvin. Then you can determine the final temperature of this argon gas, that is 308 Kelvin. So that is T2. That was the first part of this question. Then, now we want to determine the work produced by this turbine. So how can we determine this work? If you want to determine any property or any energy transfer from a thermodynamic device, you use energy balance equation. So we are going to come up with an energy balance equation for this argon. It's a turbine, argon in a turbine. Turbine has an inlet and an exit. So it's an open system, steady state open system. What is the energy balance equation for steady state open system? We have Q dot in, W dot in. This is the general energy balance equation for steady state open system. I'm going to say inlet is number 1, M dot number 1, and this M dot has specific enthalpy H1, kinetic energy V1 square over 2, and potential energy gravity times elevation Z1. And what about energy transfer out of the control volume from this turbine? Q, W, and the mass at the exit, which is number 2. This one has specific enthalpy H2, kinetic energy V2 square over 2, and potential energy gravity elevation Z2. Then let's evaluate each term one by one. Of course, you know that you don't like this kinetic energy change or potential energy change. I agree, I don't like them. Then this is a turbine. It produces power. So we have this power produced. And does turbine consume any power? No. So you neglect that. So we have a rate of enthalpy at the inlet, the rate of enthalpy at the exit. Then what about this rate of heat transfer? It's an isentropic turbine. When you have an isentropic turbine, that means there is no change in entropy. If there is a heat transfer, can entropy remain constant? No. When heat transfer goes to the system, you get more waste form of energy, entropy goes up. So we don't want any heat transfer as long as we have an isentropic process. So you can get rid of them. Why? Because by the definition of entropy, ds, the change in entropy, is going to be the change in heat over T. So if there is a heat transfer, there is an entropy change. So if you don't have an entropy change, which is isentropic process, you don't have heat transfer. Make sense? To me, yes. And what about inlet and the exit? We only have one inlet, we only have one exit, so m dot at the inlet is the same as m dot at the exit. So I'm just gonna say m dot. There's no m dot 1 or m dot 2, they are the same. Then, what else? Oh, we can move this one to the left-hand side. Then this equation becomes m dot H1 minus H2 is W dot out. So what do we want to determine? We want to determine the work produced by this turbine per unit mass. Okay, I don't like this mass, and we want to determine this work per unit mass. So let's get rid of it. How can you get rid of it? Divide by m dot, divide by m dot. Then what do you get? H1 minus H2 is not this capital anymore, lowercase. Energy transfer by work per unit mass going out of the system. So this is what you want to determine. Wait, how can we determine H1 minus H2? If it is a phase change material such as water or refrigerant such as R134A, you need to go to a property table to determine H. But what we have is argon, pure gas. If you want to determine H for pure gas, you can use specific heat. U2 minus U1 is CVT2 minus T1. H2 minus H1 is CPT2 minus T1. So let's say is CP T1 minus T2 is energy transfer by work unit mass. So what is CP? 0.5203. This one is 0.5203 kilojoule per kilogram Kelvin. T1, do we have it? Oh, 773. 773 Kelvin. T2, 308 Kelvin. So we have everything. Can you determine W? Yes. Do I know the W? Wrong. But you can calculate them, right? Any question? Any question? No? Oh yeah, all of them. All of them. $10 per page. I was kidding. Okay, now isentropic efficiencies of steady flow devices. Okay. I can guarantee one. Either in the second exam. What? You already did the second exam. The final exam. You will see isentropic efficiency. Whether it is given or whether you need to calculate that. Good to know, right? No, that there was no isentropic efficiency. That this is what we are going to calculate. And this is what we are going to learn. We haven't studied isentropic efficiency yet. The previous problem is about whether you can calculate entropy change when it is an isentropic process by using simple specific heat equation. Now we are going to calculate isentropic efficiency. Then the first thing you want to know is that, what is that? Isentropic efficiency is how close this device in comparison with its ideal, the device. So if you design a turbine, how close this turbine to an isentropic turbine, which is the ideal turbine. The ideal turbine means that we produce power, but we don't lose any energy. What is that? Isentropic process. Then why do we need those information? Let's assume that you are working for the company that produces the turbine. So there's one guy proposed that I'm going to I think that this turbine I just designed is good. So it produces the 400 kilowatt. Okay, and another guy is saying that I made a small scale, smaller turbine, which can produces only 100 kilowatt, but I think it's efficient. Now between these two, which one is better design? We don't know because one is made big, so it produces large power. One is made small, so it produces low power. How can you know one design is better than the other? By using this information, we cannot say that. Right? Then, what about in this way? In this size of the turbine, the maximum possible power you can generate. Let's say that I'm the god of engineer. I'm not. Then I'm going to design the perfect flawless turbine that only works in I don't know. So this is the best ideal turbine, same size, same conditions at the inlet, at the exit. It produces 1,000 kilowatt. And again, the small one, yeah, I can make one, small size. I'm going to use the same inlet condition, same exit condition. And I say, when I made it, since I'm the god of engineer, my turbine is going to be best, right? This is ideal turbine. And when I made it the same size, I got 105 kilowatt. Now, can you say which one is better designed? Now, isn't it clear that this one, the output is very close to the ideal case? The output is far away from the ideal case. So this one is poor design. This one is very good. Okay? So when you compare your system to its ideal system, then you can evaluate how good it is. Then what is ideal system in terms of entropy? Isentropic turbine is the ideal turbine because isentropic turbine means that there is not a single entropy increase because there's no wasted energy. That's the ideal turbine. So when I say if we have an isentropic turbine, it produces 1,000 kilowatt. The actual turbine can only produces only 40%, 400 kilowatt. So how close this turbine compared to this ideal turbine? Only 40%, because it is 400 kilowatt. The power produced by the actual turbine divided by the power produced by the isentropic turbine. This is called isentropic efficiency of turbine. Very easy to understand, right? What about here? What is the isentropic efficiency of this turbine? So in this case, okay, the isentropic turbine, which is the ideal turbine, can produce 105 kilowatt, but my turbine can produce very close 100 kilowatt. So what is the efficiency? Close to 96%. Wow, that is a very good design. So you can see, you can say this one is way better than this turbine by calculating isentropic efficiency. Make sense? So now you get the idea how to determine isentropic efficiency of a turbine. You are going to make, if you have a turbine, the way to calculate this isentropic turbine is that analyze this turbine and determine how much power it can produce. That's the first part. And the second part, now I'm going to use the same condition. Now this is an isentropic turbine. Determine the power it can produce. Now compare these two powers. Whichever larger value, greater value, go to denominator. Whichever less value, go to the numerator. That is isentropic efficiency. Okay? The same rule can be applied to any other thermodynamic devices. What about if you don't like turbines? You're going to work for a company that produces compressor, like a company that produces air conditioning systems or refrigerant systems, or the car engines where we have compressors. Compressors are very widely used. So let's say that I'm going to working for a company that uses compressor system. And what compressors does? It pressurizes fluid by consuming power. So there is a power into the system. So when I make this compressor and test it, and then it looks like this turbine consumes 600 watt of power to pressurize, let's say, air from this pressure to this pressure. Okay? So now I'm going to see how good this compressor is. So I'm going to call the god of engineer and then ask him, can you design a compressor in this, the shape, in this inlet condition, in this exit condition? So he's going to do that. Same condition at the inlet, same condition at the exit, everything looks the same. And the power consumed by this ideal compressor should be greater than 600 or less than 600. Should be less than 600. It's an ideal, should consume less for the same job. So when he did it, it only consumes 300 watt for the same compression job. So how close my compressor compared to this ideal compressor? When I say ideal compressor means isentropic compressor. So that means entropy at the inlet is the same as entropy at the exit. Then what is the isentropic efficiency of this compressor? Whichever greater value go to the denominator. My compressor consumes 600 watt, but this ideal compressor can only consume 300 watt for the same job. So what is the isentropic efficiency? 50%. My compressor is only 50% close to the ideal compressor. That's how you can determine isentropic efficiency. You can also come up with many other devices. What about pump? For the same pumping job, my pump consumes 50 watt, and the isentropic pump consumes only 20 watt. Then what is the isentropic efficiency of the pump? And my pump consumes 50 watt, but isentropic pump, the ideal pump, only consumes the 20 watt for the same pump, for the same pumping. And what is the pumping efficiency? 40%. So my pump is not very good, only 40% close to the ideal pump. Okay, get the idea? So that's the whole concept about isentropic efficiency. Then to understand this isentropic efficiency, the best way is to solve a problem together. Okay. Okay, so let's solve this problem. We have an adiabatic turbine that has an inlet, one inlet, and one exit. We have all the information such as pressure, velocity, even pressure, temperature, and even velocity. And we know the power output, which is 6 megawatt, pretty big turbine, right? And we want to know the isentropic efficiency. So how can you do that? When you want to study isentropic efficiency, always you need to have two turbines. One is the actual turbine. Actual turbine. And the other one is isentropic turbine. And you are going to compare these two. Okay? So let's talk about the actual turbine. The turbine looks like this. We have a one inlet, one exit. This one produces power much. 6 megawatt. W dot out is 6 megawatt. 6 megawatt. Okay. And at the inlet, we have 8 megapascal. Of course, at the inlet, we have a high pressure, high temperature. Steam enters this turbine because it's going to expand in the turbine. So 800 megapascal, 600 degrees Celsius, and we even have a velocity. Oh, that's interesting. 80 meters per second. If there is a significant velocity change between the inlet and the exit, then you need to consider kinetic energy change, just for your information. And at the exit, we have a 70 kilopascal and 160 degrees Celsius and 140 meters per second. Oh, there's a significant velocity increase. So kinetic energy change cannot be neglected. So let's analyze this actual turbine. How can we do that? We can use the energy balance equation. The energy balance equation is Q dot in plus W dot in plus M dot at the inlet. Inlet is number one. This one has enthalpy, kinetic energy, and potential energy. What about the energy transfer out of this turbine? Q dot out plus W dot out plus M dot that goes out, and at the exit number two, this one has a specific enthalpy, kinetic energy, and potential energy. By the way, let me know if I go too fast. Too fast. Oh, really? Okay. Good. Okay. So this time, now we usually neglect kinetic energy change and potential energy change, but since we have a significant change in velocity, so we are not going to neglect kinetic energy. What about potential energy? Somebody broke this chair. Wow, someone must be pretty pissed off, right? Okay. What I was doing. Okay, so we can neglect potential energy change, and it says adiabatic turbine. What does it mean? We have a pretty good insulation. So we neglect energy transfer by heat. So I'm going to neglect Q. Then what? Oh, it's a turbine. So turbine produces power. So we have a W dot out. And turbine does not consume power. So we don't have W in, right? I'm going to neglect that. So we have these two on the left-hand side. We have these three on the right-hand side. Then do we have velocity at the inlet? Yes, 80 meter per second. Do we have a velocity at the exit? Yes, 140 meter per second. Do we have W dot out? Yes, 6 megawatt. 6 megawatt. And do we have the specific enthalpy at the inlet? We can calculate that. It's a 8 megapascal, 600 degrees Celsius. So you need to determine the phase change process and then go to appropriate table. But usually 8 megapascal, 600 degrees Celsius, pretty high. So it should be superheat vapor. So you can check that. At 8 megapascal, saturation temperature is only 295. And what is the temperature at the inlet? 600. Far above the saturation temperature. So what is the phase change process? Number 5, superheat vapor. So there's a phase change process number 5. What about at the exit? 70 kilopascal, 160. At 70 kilopascal, saturation temperature is about 90. And the temperature is 160, much greater than the saturation temperature. So what is the phase change process at the exit? Superheat vapor again. So we have a superheat vapor here too. You can also make a property diagram, PV or TV, to determine the phase change process. We did a number of times in the classroom, so I'm not going to do that here. Actually, I don't have enough space. So, but you know how to determine the phase change process, right? So if you know that they are superheat vapor, you go to superheat vapor table. So we have 8 megapascal, 600. What is H? 3,642. So this H is 3,642 kilojoule per kilogram. What about 70 kilopascal, 160? H value is 2,798.2 kilojoule per kilogram. Now, we have everything but what? Mass flow rate. Can you determine mass flow rate? Yes. So if you solve this equation, you get mass flow rate. By the way, we don't have inlet mass flow rate, exit mass flow rate, they are the same. So M dot is going to be, I think I calculated somewhere, 7.17. 7.17 kilogram per second. So by using this energy balance equation, we were able to determine the mass flow rate. Okay, that's good. I think that was the first part, the mass flow rate of the steam. Okay, we did that. And part B, the isentropic efficiency of the turbine. You remember how to determine the isentropic efficiency? I told you, right? We are going to, determine how much power actual turbine produces, and we are going to determine how much power the isentropic turbine produces, and we are going to compare these two values. Whichever greater, go to the denominator. Whichever less is going to go to numerator. So between actual turbine and the isentropic turbine, which one produces more power? the isentropic turbine. So the isentropic efficiency that we want to calculate of the turbine can be determined by the power produced by actual turbine divided by the power produced by the isentropic turbine. We already know how much power this actual turbine produces. 6 megawatt. So we just need to find how much power this one produces, go to denominator, right? So we are going to make another turbine, in this case, isentropic turbine, that looks like this. One inlet, one exit. It produces power, how much? 6 megawatt? Not anymore. We don't know how much power it produces. It could be greater than 6 megawatt, unless this is an isentropic turbine. Of course, this is not, right? Then now the exit condition, 8 megawatt, 8 megapascal, 600 degrees Celsius, 80 meter per second. Now there's a problem. Here is important. So this turbine is going to produce more power than this one. That we know. Then, if this one produces more power, how much thermal energy in the exit should be less than here? Because this one produces more, less energy left in the steam. So whatever comes out at the exit should be less than the actual turbine. Am I right? Make sense? Because the isentropic turbine produces more power, that more power should be from the thermal energy in the steam. So we are rejecting more power from the thermal energy of the steam. So less thermal energy should be at the exit of the isentropic turbine. So out of 70 kilopascal, 160 degrees Celsius, 140 meter per second, something may not be the same at the exit of this turbine. First, 70 kilopascal. That depends on the pipe condition, which is connected to the outlet of the turbine. So that 70 kilopascal cannot change. So 70 kilopascal is here. And 140 meter per second is also the properties determined by the pipe diameter or something on the right. So it's if you use the larger the pipe, you get lower velocity. If you use a smaller pipe, you get higher velocity, right? So these two cannot change regardless of how good this turbine is. The one thing that changes is going to be this one. If you remove more power from the thermal energy of this steam, the temperature at the exit should be less than this one, right? And that temperature we do not know. So that temperature is, I don't know temperature, okay? So now we are going to analyze that isentropic turbine. Then what is the energy balance equation? The same energy balance equation here. So I'm going to repeat the same energy balance equation. So we got m dot h1 plus v1 square over 2 and is w dot out plus m dot h2 plus v2 square over 2. Now, the velocities do not change between here and there. So we have 80 meter per second, 140 meter per second. What about specific enthalpy at the inlet? Since we have a 8 megapascal 600 degrees Celsius, so H1 here should be the same. 3,642 kilojoule per kilogram. What about mass flow rate? The same, 7.17 kilogram per second. 7.17 kilogram per second. Then the only difference between this equation and that equation is going to be H2, because we may have lower temperature than this one, because we produces more power, less energy left over at the exit. Then the question is, can we determine this H2? Let's check. It depends on the condition. It depends on the condition at the exit. What do we know? Oh, 70 kilopascal. Good to know. That's it. So can you determine H from 70 kilopascal? No. So we need to find another clue. What is that? Can you find any clue that we can determine H2? What is the main difference between left and right? Left and right. What is unique on the right? What is the name of the turbine on the right? So what is isentropic process mean? Entropy S remains constant. Entropy S remains constant. S1 is S2. Then, can you determine S1? Yeah, because we know 8 megapascal, 600 degrees Celsius, it's a superheat vapor. So what is S1? 8 megapascal, 600 degrees Celsius, S1 is going to be this value, 7.0206 kilojoule per kilogram Kelvin. Oh, good to know. So now we know S2. S2 is this number. Now we have S2, and we also have P2, 70 kilopascal. If you know pressure and entropy, can you determine H2? Yes, we can. Now we can do that. So, how can you determine H2 if you know pressure and entropy? It depends on the phase change process. Wait, didn't we say it's a superheat vapor? Yes, in the actual turbine. In the isentropic turbine, not anymore. So we need to determine the phase change process one more time. How can we do that? By using a property diagram. And we know pressure and entropy. So I'm going to make pressure and entropy T at this P, 70 kilopascal. We can make T as diagram. Looks like this. To complete this TS diagram, we need to know T set SF SG. Where can you find T set SF SG? From a property table at 70 kilopascal. So let's go there. At 70 kilopascal, there's a SF, there is a SG. So I'm going to write them. This is SF, this is SG. So SF is 1.1919. SG is 7.4797. Okay. Then, can we determine the phase change process? I think yes. What is entropy? 7.02. So let's find this number on this TS diagram. 7.02 is greater than this. Okay. But less than this. So where is our system between SF and SG? What is our system? Number 3, right? Number 3, saturated mixture. If you have number 3, can you determine its enthalpy? Yes, by using what? Linear interpolation. So H2 can be determined by linear interpolation. HF plus quantity X times HG minus HF. Then what is HF? And 70 kilopascal HF is this one, 376.7 Hg, 2660, and HF, again this number, 3376.7. But we are missing one property, quality X. And is there any way we can determine quality X? Yeah, we can use another linear interpolation, not with H. Another one, S. S2 is SF plus quality X times SG minus SF. So what is S2? 7.0206. What is SF? 1.1919. SG. 7.4797. SF. 1.1919. Can you determine X? Oh, yes, we can. 0.923. 0.927. I'm sorry, not 3. And this one goes here. Can you determine H2? Yes, we can determine H2. If you do, we get 2493.32. $2493.32 kilojoule per kilogram. That is H2. Now we have H2. That goes. Oh, I don't like this, but we got no space. Going up right here. Let H2 go to this energy balance equation. Now, can you determine W dot out? Yes, we can. Now we have everything but turbine power produced. So we can determine W dot out. That is 8.189 megawatt. And I'm sorry for that again, since we got no space. So this number goes flying here. 8.189 megawatt. Now the isentropic turbine efficiency is 73.3%. If I give you this problem in the final exam, can you solve it? It takes time, but too bad. Please solve this problem by yourself after this class. Make sure that you have no, the problem, solving this problem, because there will be isentropic efficiency in the final exam for sure. I can guarantee that. It's not 99%, it's 100%. 100%. You will see isentropic efficiency. Okay? So we have 10 minutes. The last part of is too fast. Good. Okay. Good. Okay. The last part of entropy is going to be entropy balance equation. Entropy balance equation. What is entropy balance equation? I have 1, 2, 3. 1, 2. Oh, there should be one more. So I have one slide, second, and third to explain entropy balance equation from the book. But I'm going to give you 1-page summary of entropy balance equation. Why don't we need that? So then why do we study entropy? Because we know entropy can show how much energy has been wasted in your process. So when there is a change in entropy, which is greater than 0, that is the typical thermodynamic process, which has irreversible process. Any process. Okay, then entropy change is 0, that means reversible process. When entropy change go to below 0, impossible process. Okay, that we know. So entropy should increase all the time, unless it's an isentropic process, but it is unlikely to see an isentropic process in the real world, right? Because whenever there is a process, could have irreversibilities. So most processes are when there's an entropy increase. So let's talk about that. Okay, now we got that there should be entropy increase. Can we quantify that entropy increase? Yes. By how? By using entropy balance equation. But is there any other balance equation that we studied? Yes, the famous energy balance equation. What is this energy balance equation? How this energy balance equation is developed? Based on the conservation of energy principle. So when energy goes into a system and when energy goes out of a system, it should be the same as the change of energy of the system. That we know when you eat 3 hamburgers in the morning, when you poop 2 hamburgers in the afternoon, how many hamburgers in your belly? Nothing, because they are digested, right? Yeah, there's one left over in the belly, right? So that is the conservation of energy principle. Can we use the same rule for entropy? No. Why? Because of this. Because entropy always increases. Then, what about if we include the increase of entropy, which is entropy generation? If you include in this equation, then you can come up with entropy balance equation. Entropy in minus entropy out cannot be the change of entropy of the system, but if we add this one in this equation, then we can use entropy balance equation. By using this entropy balance equation, one thing that we can calculate is going to be how much entropy has been generated. Isn't it nice? Yeah, then we just need to know how to determine S in, how to determine S out, how to determine the change of S of the system. Are they difficult? Not at all. Not at all. So let me, go over together how to determine each term. The first one is the right-hand side. Can we determine the change of entropy of a system? Yes. How do you determine the change of weight of your body? You measure your body, today, and you measure your body weight tomorrow and calculate the difference. That's the weight gain you get, right? So the same thing. And the change of entropy is going to be entropy at the final state minus entropy at the initial state. That's how you determine the change of entropy, right? The weight after eating, the weight before eating, that's the weight gain by, the eating, right? Then what about entropy transfer? This one. Entropy transfer can be, by energy transfer. How many energy transfers that we studied in thermodynamics? There's an energy transfer by heat, which is Q, and there's an energy transfer by work, W. There's an energy transfer by mass, energy transfer by mass, right? So 3 of them. Then, is there entropy transfer due to heat transfer? By the definition of entropy, change in entropy is going to be change in heat transfer over temperature. Oh, there is the answer. The entropy transfer by heat is going to be this one. Q in over temperature. Oh, that was simple. What about entropy transfer by work? When electricity goes from one location to another location, is there waste energy developed? No. There's electricity, goes to electricity, so nothing happens. So there is no entropy generation. So entropy transfer due to energy transfer by work, nothing. Because work is useful energy transfer, right? What about entropy transfer by mass? Oh, it's simple. Mass that goes into a system times specific entropy of the mass. Difficult? Not at all. Oh, where is it? There's a mass times specific entropy. Then we can switch this one to mass times mass at the final state times specific entropy at the final state minus mass at the initial state times specific entropy at the initial state. We got 2 minutes of that. That's plenty enough. Then let's combine them. Entropy transfer in can be either entropy transfer due to heat, entropy transferred by the mass. So let's say it's going to be Q in over T, and this one plus M in times S in, and we have an entropy transfer out, minus Q out over T minus M out times S out, plus entropy generation should be M2S2 minus M1S1. So this is entropy balance equation. But that is not the end of the story. In thermodynamics, we studied two systems, a closed system and an open system. So let's look at this equation, one for a closed system and one for the other in an open system, because this equation as is looks complicated. I don't like that. So I'm going to assume that we have a closed system. That means there's no mass transfer in and out. And let's simplify this equation. That's Q and in together, we can say net heat transfer Q. We can do that. So net heat transfer Q divided by temperature, and there's no energy mass transfer in and out. So we only have energy entropy generation. It's going to be, it's a closed system. M2 is the same as M1. So it's going to be mass times S2 minus S1. That's an entropy balance equation for a closed system. Looks much simpler than this one, right? What is the other system? The one in chapter 4, steady state open system. When you have a steady state open system, is there initial mass and the final mass? No, there's nothing changed in time. So you can neglect the right-hand side of this equation. So what do we get? You can combine these two and say net heat transfer over temperature plus M in S in minus M out S out plus entropy generation is 0. Wow, that's simple. But when we have a steady state open system in chapter 4, we used the rate form of energy balance equation. That means that add a dot on top of it, we can do the same. Q dot, M dot, M dot, and S dot gen. So that is the rate of entropy generation. So these two equations are entropy balance equations. So on next week, Tuesday, we are going to use these two equations to determine either entropy generation or the rate of entropy generation. That will be the end of chapter 6. Any question for today? No? Okay, then see you next week.